Folks, so welcome to Dr. G's What the F Prime lecture series on physics, mathematics, and chemistry. And today we're going to be looking at a really cute section in chemistry called stoichiometry. I love this word, stoichiometry. What is it? Well, if you ever look at a chemical reaction, we have a series of reactants put together in a little vessel, and we could add in some energy to that, and as time progresses we have products being produced. So really what we're doing here is tallying up or balancing the masses, or basically the particles that are involved in the different processes, both reactants versus products. So that's really nothing more than the accounting of reactants versus products in a chemical reaction. Just mentioned, the accounting of the masses when we look at reactants combining to form products in a chemical reaction. And here's a beautiful illustration of what we mean. Firstly, right in the middle of your picture, it says the law of conservation of mass. And you'd remember from your childhood, so to speak, it's always been drilled into your head that mass cannot be created or destroyed. So in any chemical reaction, the mass has to be conserved. So what we start off with is what we must end off with. We cannot lose mass in the universe. And that's interesting. So we have here a very simple reaction. You've got sodium hydroxide solution there, and you've got a copper sulfate solution, which is that beautiful blue color, not this blue, by the way. And so the reaction proceeds, but take note of the mass. The mass of this entire thing is 67.25 grams. So we get these reactants to mix thoroughly, and we get some sort of chemical reaction going. And in the process, you have copper hydroxide precipitate. You should want to review the word precipitate. So there's a chemical reaction. There's a change in the reactants to produce products. The products here is actually sodium sulfate in solution, as well as the copper hydroxide precipitate. So the reactants are quite different from the products. But what remains constant is the mass. You see, the mass of the reactants is exactly the same as the mass of the products. So that's what we mean by the law of conservation of mass. And the idea behind stoichiometry is to basically balance the books, balance the chemical reactions. So if we know the number of particles or the masses of the reactants, we should be able to predict the products either in mass or in volume. And that's the idea behind this section called stoichiometry. Now, in order to do any chemistry, I think we need to understand the differences between the fundamental building blocks of matter and higher order particles. So at the very heart of things would be something called the atom. So it's a cute little illustration over here. So we have the helium, the atom itself, and we know that atoms can be deconstructed into protons, neutrons, which bind together to form the nucleus, and the electrons, which are negatively charged, would orbit around this positively charged nucleus. So that's the sort of picture we have of the atom, which is a classical picture, by the way. And then when atoms combine, and if you look at the second case here, when a hydrogen atom combines with another hydrogen atom, you produce what we call a molecule. And so this is the hydrogen molecule. And if you think of hydrogen gas in the gaseous clouds all over the universe, and those clouds consist of hydrogen, and that is H2. And you could also get more complex structures, and these are compounds. A good example, a very simple one that we're familiar with, is H2O. Another word for that would be water. So we have two atoms of hydrogen combining with a single oxygen atom to produce a water molecule. A series of those molecules is what we refer to as the water compound. Right, so please distinguish between the atom, the molecule, and also, if you recall, an ion, I-O-N, ion or ions. I just want to emphasize the whole idea of conservation of mass, conservation. So basically what you start off with, so before the reaction takes place, and what you end up with after the reaction reaches completion should be constant in this case. So if you have a look very carefully over here, we have hydrogen molecules. There we got H2 and we got 2H2. You see two hydrogen molecules, and this combines with a single oxygen molecule, O2. And these are what we call diatomic gases, if you remember from grade 10. And if you get two hydrogen molecules reacting with a single oxygen molecule, what it does produce are two water molecules, or two H2O molecules. Now, if you start telling up the atoms, not the molecules, but the atoms, because you think, oh, well, if I add the numbers here, there'll be 2 plus 1, and you're producing 2. That's not quite the same. No, you have to be very, very careful what you talk about here. So what we have to do is break it down. So on the left-hand side, we have 4 hydrogen atoms. You agree with me? These are the yellow dots that you see there on the left-hand side. On the right-hand side, the products, because we have 2 waters, we also have 4 hydrogen atoms, which means the number of hydrogen atoms are actually conserved in this reaction. If you look at the left-hand side in terms of the reactants, we have 2 oxygen atoms. On the right-hand side, the products, we also have 2 oxygen atoms. So the number of oxygen atoms are conserved. But the best way of actually seeing it is these atoms actually are endowed with mass. They have mass. So if you have the atoms being conserved on the left-hand side as well as the right-hand side, then the mass does not change. And we say that the system is balanced and mass is conserved. Pretty straightforward. Conservation of mass, does it always apply? Well, in the known universe, yes. And here's another very simple example here. CH4, let's recall the common name for CH4 would be methane. And so when methane reacts with oxygen, it produces carbon dioxide, CO2, plus water. And that sort of reminds me, these organic compounds, CH4. And if you look at petrol, I always like the idea that when you start up a car, and you've got petrol that's igniting, and you look at the little droplets of water that come out of the exhaust, this reminds me of a very similar reaction. So the petrol is nothing more than an organic compound. It's basically igniting in the presence of oxygen to produce CO2 and water. So let's have a look here and see whether everything tallies up. So we have 2 oxygen molecules, but how many oxygen atoms? So if you have a look here, we have 4 oxygen, I'm going to write this as oxygen atoms. 4. Okay, these are the red ones. That's the reactants. So if you look at the right-hand side, the product, how many red atoms do you see? Well, you expect that. You see 4 oxygen atoms. If you go to the left-hand side, you've got how many hydrogen atoms? The hydrogen atoms are the white chappies all over this place you see there. So there are 4 hydrogen atoms here. So there are 4 H atoms. And then on the right-hand side, for as sure as God made little apples, how many hydrogen atoms do you expect on the right-hand side as the products? 4, of course, exactly. Now you're getting the picture. So there's 4 hydrogen atoms on that side over there. And then we have that black sphere or gray sphere, and that represents what we call the carbon atom. So we have 1 carbon atom on the left-hand side, and no prizes for guessing here, we should have 1 carbon atom on the right-hand side. So tallying up the atoms, that's conserved, hence mass is conserved during this chemical reaction when methane burns in the presence of oxygen to produce carbon dioxide and water. Excellent. Now, it is really difficult to speak of mass because, you think about mass, what are we referring to? We're looking at, is it the atoms, is it the electron, is it the proton, is it the neutron, is it the molecule? So we introduce what we call the mole concept in chemistry. So chemists love to speak of moles rather than masses. And so what we do is we settle on a unit called the mole, and the mole is defined as exactly 12 grams of carbon 12. So if you look at the periodic table, carbon is in group 4, right? And if it has a relative atomic number of 12, so 12 grams of carbon is precisely 1 mole. And so what actually happens is, when we look relative to carbon, we measure all the other elements and their masses. So if you look at copper atom, if you look at the periodic table, copper, the atomic mass of copper is 63.5 grams per mole. So if you want 1 mole of copper, you should measure out 63.5 grams. So 63.5 grams of copper is exactly 1 mole. 12 grams of carbon is exactly 1 mole. So we need to look at the mole concept very, very closely in order to make any progress when studying stoichiometry. To ask you what's the most important number in your life, and most people will say, well, it's my birthday, or it's my cell phone number, well, or my bank account number. Now, to physicists and to chemists, we have all these very interesting numbers like Euler's constant, or the value of pi, or the Hubble constant. And for Einstein, I think the speed of light was a very, very important constant. Now, in chemistry, there's a number that comes up, and you see that on your screen right here. It's 6,02 times 10 to the power 23. This is a huge number, and it's called Avogadro's constant, Avogadro's number. Okay, named after the Italian mathematical physicist Avogadro. So normally what we do is we write this as Na is equal to 6,02 times 10 to the power 23. But what is it measuring? What are the units for this? Well, what it's actually measuring are units, and these units could be atoms and they could be molecules, or ions. So it's very important that we specify whether we're working with an atomic compound, a molecular compound, an ionic compound. So that'll give us an idea of the particles that we are measuring. But for now, it's 6,02 times 10 to the power 23. Try to get a feel for this number, 10 to the power 23. An absolutely amazingly huge number. I've seen calculations where if you had to mix up Coke, a liter of Coke, into the ocean and let that mix up and just dissolve into the ocean's water, and then a couple of weeks later took a sample of that seawater, how much of that, should I call it, Coke atoms from that Coke bottle would you still find in that sample? It's interesting. I mean, these numbers are absolutely huge. So just to get a feel for that, it's always good to read up on these large numbers. And the name Dirac, Paul Dirac, with its large number hypothesis, no relation to the Avogadro constant, that is something you should also look up. Just had to include here, not the picture of Avogadro, but really in context. Hey ladies, take my number. Yeah, so 6,02 times 10 to the power 23. Yeah, that's going to be a nice number you want to put on your t-shirt. And the older folk amongst us, I mean the adults amongst us, if you're looking for a tattoo, that's the number to tattoo. 6,02 times 10 to the power 23. Remember the constant, Avogadro's number. Okay, so you've been waiting for this moment, and now I'm going to actually show you how to calculate the number of moles if you're given the mass of a certain substance. So right here you see a very, very important formula. You've seen this probably as early as grade 10. The number of moles N is equal to M, which is the molar mass, and the mass of the substance in grams, divided by the molar mass in grams per mole. And I think this is absolutely crucial that you understand that. So to work out or calculate the number of moles, it's the mass in grams divided by the molar mass in grams per mole. Okay, so what we're going to do next is to do a few calculations and see how we get to these. Just to remind you, just took a little shot of the periodic table. So what we see here is hydrogen. It has a molecular mass or molar mass of 1. And you look at the larger numbers now. If you look at the periodic table, if you look at the smaller numbers at the top here, these numbers at the top, what are they? I mean, that's the proton number, or what we call the atomic number, the number of protons in the nucleus. The larger numbers that you see at the bottom here is really nothing more than the atomic mass. So hydrogen has an atomic mass of roughly 1, carbon 12, and oxygen is roughly 16. And you're thinking, well, why are these numbers not exactly like 12.00000 or 15.000 or 16.0? And that is due to the existence of what we call isotopes. Remember that, isotopes. Well, for the purposes of this lecture, the first thing they ask us to do here is calculate the molar mass of water, the molar mass of water. So if you have a look very carefully, and it's very important that you write neatly, you write properly, and you also write clearly. So if I want to work out the molar mass of water, all I'm going to do is say take capital M, just like that, and I'm going to go subscript H2O like this. It tells the person reading my work that I'm working out the molecular mass of water. And this is what I would do. I know that water consists of 2 hydrogens plus 1. Now watch the way I write the oxygen. I actually like to underline that so it doesn't look like 10, but 1 times O for the oxygen. The molecular mass of hydrogen from the periodic table is 1 gram per mole. The molecular mass of oxygen is roughly 16 grams per mole. And please don't use your calculator here. 16 plus 2. And now we worked out the molecular mass of water, which is 18 grams per mole. And this is something that you want to really commit to memory or remember for a long time, because we work with water all the time. In chemistry, in physics, in engineering, and problems in mathematics as well. And of course, you've got to have a minimum of 8 glasses of water per day, they tell you. Of course, it depends on the volume or capacity of that glass. The next question, very simple one. Calculate the molar mass of ammonia. Now, I don't have the periodic table in front of me, but it would be really cool if you had a periodic table up on your wall, or you can access one quite easily on your cell phones. So ammonia, watch again how I'm doing my presentation. The molecular mass is NH3. This is the beautiful way of writing. 1 nitrogen. How many hydrogens? Well, it's 3H. And if you look at the periodic table, the atomic mass, the nitrogen is going to be 1, and that's going to be 14 if I remember from about 3 decades ago. And hydrogen would be there, so that would be 17 grams per mole. Straightforward, no thinking, absolutely amazing. So if you can send a text message over WhatsApp, if you're on Instagram, this stuff is straightforward. For those of you who had forgotten what a periodic table is or looks like, so there we have a really beautiful one out here. It's very colorful as well. I like this bit here. It tells you or points out to you the radioactive substances that you'd find on the periodic table. And what I love about it, most people actually tend to forget that, out of all these elements that we've seen here, the ones on Earth that we have in their natural state and at room temperature, we just have 2 liquids in all of these, or amongst all of these elements. So which are they? Let me give you 1, 2, 3, 4, 5 seconds, and the answer is mercury. The symbol for mercury is Hg, if you remember. And there's one more liquid that's sitting here, right over here. I'll give you a clue. It's in group 7. It's part of the halogens. And the answer there is bromine. Beautiful. All right, excellent. So what I would say is spend some time learning up the properties of elements, their uses. Just fill that brain up. They tell us that the average person uses just about 5% of their brain. So if we just put in the periodic table here, that'll go to 5.00001%. But let's just make use of that beautiful, beautiful computer that we all walk along with. All right. So, excellento. Okay, very similar question right now. Calculate the molar mass of calcium carbonate. Calcium carbonate, again, stick to the notation CaCO3. So it'll be 1 calcium, 1 carbon, plus 3. I underline the oxygens like that. So we go very simple. And if you remember, calcium, if you have a look carefully, has a molecular mass of atomic mass of 40. So you get 1 times 40. Carbon was 12. 3 into 16. So we go 40 plus 12. That's 52 plus 3 times 16 is 48. And what do you know? That's 100 grams per mole calcium carbonate. Straightforward. So if you have a look here, they're just trying to make life a bit difficult. Calculate the molar mass of ammonium sulfate. Ammonium sulfate. So it's NH42SO4. That's a good question, by the way. So if you go molecular mass here, we're going to go NH42SO4. That's going to be 2, watch this, of that plus 1 sulfur plus how many oxygen? 4 oxygens. So split this up even further. So that's 2 nitrogens. But how many hydrogens? 2 times 4. So that becomes 8 hydrogens plus 1 sulfur plus 4 oxygens. Put in the numbers 2 times 14 plus 8 times 1 plus 1 times 32 plus 4 times 16. So that's going to give me 28 plus 8 plus 32. What is 4 times 16? And no calculator, please. It's 64. So we got 32. That's going to be me 40. 40, and that's going to give me 68 plus 64. And that's going to give me, well, 132 grams per mole. We in the zone, yeah? And that's looking really good. So ammonium sulfate, molecular mass, 132 grams per mole. But I think what we need to emphasize here, and I think this is the reason why this question was asked, is the way we deal with the 2 out here. All right. So it's actually multiplying that entire bracket. So the molar mass of copper sulfate dot 5H2O. What does that mean? Well, this is hydrated copper sulfate crystals. They are a beautiful, beautiful, stunning blue. So you've got these copper crystals, and in them you have this water, or the presence of water, that gives this beautiful color. So they want the molar mass of copper sulfate dot 5H2O. Now in mathematics, when you see a dot, you will quickly say, well, that is multiplication. Not with chemists. No, no, no. In chemistry, that dot represents addition. So the molecular mass of copper sulfate, hydrated copper sulfate, H2O, is going to go 1 copper sulfate plus that dot is plus 5 waters. So copper, if I remember, was 63.5 from about 3 decades ago when I was doing this section, plus 1 sulfur, which was 32. And how many oxygens do we have here? 4 into 16 plus 5. Well, let's look at the entire water molecule. We now know that the molecular mass of 1 water molecule is 18 grams per mole. So this is just 5 times 18. And then you could just add this up to your content, 63.5 plus 32 plus 64 plus 5. That will be 90. Is that right? And you can play around with this, and you can actually sum this up, and that'll give you a single number. So that's 63.5, that's 98 plus 90, and I'm not going to use a calculator there, so I'm going to go through this slightly slower. And so that's 0.5, and we got 3 and 8, that's going to be 11, so then we're going to carry 1, 9 and 9, 18, and 119 and 6 is 25. 251.5 grams per mole. Would that be right? Let's have a look and see. We just have a look at that again very carefully. So we have to have the 0.5, and then we go 3 and 8, 11. We're going to carry 1 over. That's 7 and 9, 16. 16 and 9 is 25. That looks about right to me. So 251.5 grams per mole for copper sulfate, hydrated. So the dot does not mean multiply, it means add. If you read this, just calculating the number of moles. So calculate the number of moles of 36 grams of water. So you recall very quickly, and I think this is important to store in your memory, the molecular mass of water was 18 grams per mole. The formula for calculating the number of moles is mass over the molecular mass. In this case, it's water, so it'll be the molecular mass of water. Mass is 36 grams. That's given. And this is 18 grams per mole. 36 over 18. Do not use your calculators. That's going to give you 2 moles. That's your final answer. So 36 grams of water is equivalent to 2 moles of water. Similar to the previous question, here we've got 20 grams, which is the mass of calcium carbonate. But recall, what is the molecular mass of calcium carbonate? Calcium carbonate CaCO3, and if you remember, this was 100 grams per mole. Just store this information in your minds, your beautiful minds. Formula for number of moles is mass over, in this case, the molecular mass of calcium carbonate. The mass was 20, and that's 100, so that's 2 over 10, which is 1/5. So this gives me 0.2 moles. So 20 grams of calcium carbonate is the same as 0.2 moles of calcium carbonate. Very carefully, a vessel contains 2 moles of sulfuric acid. Now, this is interesting. We don't have the formula, my goodness, but you learned this way back in grade 10. What is the formula for sulfuric acid? And you'll remember very quickly, it's H2SO4. So calculate the mass of sulfuric acid present. So we know the formula is number of moles is mass over molar mass. So that's over 1. So if I cross multiply, then mass, m times 1 is m, and that must equal to number of moles times molar mass. I've got the number of moles is 2. What I'm missing is the molecular mass of sulfuric acid. So it's H2SO4. It'll be 2 hydrogens, 1 sulfur, and how many oxygens? 4 oxygens. Hydrogen is 1, sulfur is 32, and oxygen is 16. So we've got 2 plus 32 plus 64. Am I right? So that gives you 34 plus 64, and that should give you a beautiful 98 grams per mole. Is that right? 96, 98. That's perfect. So if you go back to this formula, what are we calculating? We're looking at the mass. We're looking at the mass is the number of moles times that. So that gives you 2 times 98. What is that going to be? 2 8s are 16, so 6 carry 1, 2 9s are 18, and 1 It's 196 and the units would be grams. So 2 moles of sulfuric acid is the same as 196 grams of sulfuric acid. Isn't that simple, beautiful, straightforward? And a very similar question, but I think what they're really testing is, do you know, firstly, the formula for aluminium oxide, or some would say aluminum oxide? So we have 2 moles, so we want the mass, by the way. You need to understand what the question wants. You know, it's many a time I see students read the question and then start plugging stuff into a formula, and suddenly in the middle of the calculation, then you ask the question, what am I solving for? You know, it's equivalent to getting into a car, driving for about 150 kilometers, and then suddenly asking yourself, where am I going? So you got to get some direction right at the beginning. So we want the mass, okay? We want the mass. We've got moles. So the only formula that's linking mass with moles for now is number of moles is mass over the molar mass. So if I want the mass, as I mentioned before, we cross multiply. M times 1 is M, N times molar mass. So I've got the number of moles, that's 2, that's M. I need the molecular mass of aluminium oxide. And now you are stuck. What is the formula for aluminium oxide? Aluminium oxide, go back to your notes in grade 10, is Al2O3. 2 parts aluminium, 3 parts oxygen. So the molecular mass of Al2O3 would be 2 aluminiums plus 3 oxygen atoms. 2 times aluminium is 23, and 3 times 16. So that tells me that is 46 plus 48. 6, that's 94, is that right? 6 and 8, 14. That's 94 grams per mole. No need for the calculator. Number of moles is 2, and then we're going to multiply that by 94. And that gives me 188 what? Grams, because that's what we want. We want the mass. The mass here is measured in grams. It's 188 grams of aluminium oxide. It's interesting that we can do these things without a calculator. This question is quite interesting. You know, moles, and then you've got Avogadro's number. So you're given 36 grams of water, and ask you several questions. And one of the first questions, calculate the number of moles of water. Oh man, this is crazy. It's simple. So the number of moles of water, that'll be mass over molar mass. If you remember, it's 36 grams that was given to us. And the molecular mass of water was what? 18. So what is 36 over 18? That is 2 moles. 2 moles. So what we started off is 2 moles of water. Now, let's just try to remember this question. It says the number of water molecules present, the number of oxygen atoms, number of hydrogen atoms, and the number of atoms present, the total number. So the first thing we want to do is look at the number of molecules present. Molecules present. And then we're going to split this up into atoms, oxygen, hydrogen, and finally the total number of atoms. So what we're starting off with is 2 moles of water. Okay, so just keep that in mind. If you look at Avogadro's hypothesis or law, it says 1 mole of any substance contains exactly 6,02 times 10 to the power 23. I'm going to use the word units. And the units can be replaced with the word atoms or molecules or ions. All right. So the first question they asked was 2 moles of water. 2 moles of water. How many water molecules is that? Okay. So if we have 2 moles of water, how many H2O molecules? Well, here we go. 1 mole of water equals 6,02 times 10 to the power 23 water molecules, right? That's the unit we're looking at. So, no prizes for guessing, no Nobel Prize in chemistry. So 2 moles of water would be 2 times Avogadro's number, water molecules. Do you understand that? So if 1 mole is 6,02 times 10 to the power 23 water molecules, double that, you have double the number of water molecules. Okay, that's a structure of a water molecule. A single oxygen atom combining with 2 hydrogen atoms. The next question was an interesting one. And the question they were asking is, what is the number of oxygen atoms in 36 grams of water, or equivalently 2 moles of water? So let's look at that more closely. What have we got so far? We've got 2 moles of water. Right, that was 36 grams, 2 moles of water. And we've already said that was 2 times Avogadro's number of water, watch the word, molecules. The next question we want to tackle is how many oxygen atoms are in that number of water molecules. So you remember from my little diagram that I had here, each water molecule consists of 1 oxygen, and that's covalently bonded to 2 hydrogen atoms. So for every water molecule, we have 1 oxygen atom. So the number of oxygen atoms in 2 moles of water, it stands to reason, should that not equal to 2 times, right, atoms of oxygen? So the number of oxygen, so here's the thing, for every 1 water molecule, you have 1 oxygen atom. So if I got 2 times 6,02 times 10 to the power 3 water molecules, then I should have 2 times 6,02 times 10 to the power 23 oxygen atoms. Does that make sense? Please read through before moving on to the next slide. So we worked out the number of oxygen atoms. The next question, and we expect this, how many hydrogen atoms do we have? So let me just write that down to remind you. How many hydrogen atoms do we have? How do you spell have? Have in 2 moles of water. Well, let's just go back. There's the oxygen, there's the hydrogen, and that's a water molecule. So for every 1 water molecule, how many hydrogen atoms do you see? Well, I can clearly see 2. So if 2 moles of water, let me reason this out very carefully, 2 moles of water consists of 2 times 6,02 times 10 to the power 23 water molecules. And if each water molecule consists of 2 hydrogen atoms, then it's pretty obvious that we should take this number of water molecules and multiply that by 2 to get the number of hydrogen atoms. I'm not sure if this gets any easier than what I've just written down here? Well, some of you are seeing this for the first time, so you've got to read this a couple of times, process that, and make sure you understand. And I think it comes down to the very simple things like the difference between an atom, a molecule, and an ion. So you've got to go back and revisit the time you first came across these concepts and actually understand what's being referred to. The last part of the question is a very simple one, that is, calculate the total number of atoms in 36 grams, or the same as 2 moles of water. So let's start working this out. So let's start telling things up. So we've got oxygen, we've got hydrogen like this, and so total number of atoms, write neatly, equals to the number of oxygen atoms plus the number of hydrogen atoms. The number of oxygen atoms, let's remember that. Let's just recall that. Number of oxygen atoms, because we had 2 moles, it'll be 2 times Avogadro's number there. And then the number of hydrogen atoms, this guy over here, would be, because for every water molecule, or for every oxygen atom, we have 2 hydrogen atoms. That'll be 2 into this number over here, to power 23, not minus 23, but 10 to the power. So that's 4, and that's 2, so that's going to be 6 times 6,02 times 10 to the power 23 atoms. And that those atoms are a mixture of oxygen and hydrogen. So that gives you that nice number that you see there. Or in a more compact way, you'd like to write this as 6 Na atoms, where Na is 6,02 times 10 to the power 23. Okay, so many of us have studied gas laws, and we speak of volumes, and we speak of liters, but it's also, we know that 1 liter is the same as 1 decimeter cubed. So it's interesting that we also speak of STP, standard temperature pressure. What is that? STP. What are the conditions for standard temperature pressure? Well, the temperature is about 298 Kelvin, and the pressure is just around 101,3 kilopascals, or 101,300 pascals. So when you see STP, standard temperature pressure, and then those constants are given as 298 Kelvin, and the pressure is 101,300 pascals. Now, it's important here that you learn this up. It says that at STP, 1 mole of any gas occupies a constant volume of 22,4. I don't like to use the word liters, but I say a constant volume of 22,4 decimeter cubed. So volume of a gas at STP is 22,4 decimeter cubed. It's the sort of number that you actually want to remember. 1 mole of any gas, 22,4 decimeter cubed at STP. Okay, so let's have a look at this one. So calculate the volume that 8 grams of oxygen gas occupies at STP. Now, a little rule here, and a very simple rule. When you see mass, if you look at volume, convert everything to moles. Chemists love moles. So the 8 grams of oxygen, we ask ourselves, how many moles is that? So number of moles is mass over the molar mass of oxygen. Now, you've got to be very careful here. So it's 8, but oxygen is O2. So O2, let's just say molecular mass of oxygen will be 2 times oxygen is 2 times 16 grams per mole. So that is 2 over 32, which is 0.25 moles, which is a quarter mole. Now, what's the rule? The rule says 1 mole of any gas at STP occupies a volume of 22,4 decimeter cube. So this is the way I'd like to do this one. It's really a ratio. So 1 mole at STP is 22,4 decimeter cubed. We don't have 1 mole. We got 0,25 moles, and that is going to occupy X, a volume of X. And what we do then is to just cross multiply in some sense, if I think of it that way. So X times 1 is X. So the volume occupied will be 0,25 times 22,4 decimeter cubed. And you can check this out. It turns out to be 5,6 decimeter cubed. So 0.25 moles of oxygen, or 8 grams of oxygen, occupies a volume of 5,6 decimeter cubed. So that's pretty straightforward at STP. Look at this question over here. It's not really challenging as much. So it says, what is the mass of 56 decimeter cubed of nitrogen gas at STP? So what we're looking for is the mass. We have the volume is 56 decimeter cubed. And the only formula we have now is number of moles is mass over molar mass. The molar mass of nitrogen, do you recall that? That is 2 times nitrogen N, so it's 2 times 14, which is 28 grams per mole. So if you look at the formula, we want the mass. So here the mass is number of moles times the molecular mass. So what we have is the molecular mass, but we don't have the number of moles. Strangely enough, we have the volume. So if you think about this very carefully, at STP, what do we know? 1 mole of any gas occupies a volume of 22,4 decimeter cubed. But we've got 56 decimeter cubed. So X moles occupies 56 decimeter cubed. So if we cross multiply, we'll get 22,4 X is equal to 56. So X would be 56 all over 22,4. 56 all over 22,4. Please check this. Turns out to be 2.5 moles. Now that's interesting, okay? Because what we've taken is the volume that we're given, and we've now found out the number of moles of nitrogen at STP, and that's it. So if we go here, the number of moles is 2.5, and we've got 28 grams per mole, so the mass is 2.5 times 28, and that gives me a neat figure of 70 grams. So what are we saying? We're saying that 70 grams of nitrogen at STP gas will occupy a volume of 56 decimeter cubed. This is straightforward. It's very, very simple. All you have to do is realize what's given, what the question is asking, and to remember little odds and bits which are intrinsically given, like STP. You know, they're not going to tell you it's 1 mole of any gas and the number 22,4. You've got to make that connection, and that comes with lots of practice. You know, it's been a nice little excursion into stoichiometry, but this is just the beginning, and this is just part 1, an introduction to the fundamental concepts. I'm looking forward to putting up the second part of stoichiometry, where we now actually set out to balance equations and then to predict or what we call the amount of the yield of product given the reactants that are put into this vessel or container. So this becomes a really exciting section, and it's a fundamental section even in matric, but not just, as I always say, don't learn to pass the exam. Learn for life. I mean, you might be working out as a chemical engineer or a chemist. You never know. So learn for life, not to pass an exam.